Hello, this is 6.1. Oh shoot, I'm not sorry. It's not 6.1, it's 7.1, in which we are dealing with systems of equations. Okay, and specifically 7.1 is going to be solving them through substitution. Okay, so this is something you've done in Algebra 1, you do it in Algebra 2, probably even a little bit actually geometry, and it comes back up again in precalc. So in this time in precalc, it's a really short, simple, quick section for this. You've done these solving systems of equations using both substitution and elimination. So the substitution will be the first one. We will get to elimination, and then we'll start solving them through other means. We'll teach you how to do them when there's more than two variables within that equation. So again, you've done this. The first one's going to be super quick, super simple, super easy to kind of bring you back into what solving by substitution looks like. So when I label my equations, I like to label them by 1 and 2. I can kind of talk about them as an equation then, and we'll reference 1 and reference 2 versus trying to say that, I'm just writing this a little bit bigger, versus trying to say that entire equation out to reference what I'm talking about. Okay, and again, there are guided notes for this section, so if you want to go grab the guided notes, it's just kind of a nice helpful way to kind of run you through some of these and show you some things off to the side that I want you to be thinking about. So our first step when we're doing this is we need to decide which equation we want to start with. You have to decide which one is going to be easiest to manipulate and which that you're going to solve for one variable or the other. So I would have to isolate or get by itself x or y or x or y. Now, there's no wrong answer most of the time. One answer will just be more complicated, maybe take longer, be more prone to making mistakes than the next. I'm going to choose equation number 2 to start with for no other reason than the fact that if I start with this equation, I will end up having, let me grab my marker. I will end up having all positives to solve with. Not that I don't trust you with negatives, but when you have all positives, it just makes things a little bit easier. So if I start with this one, this x minus y equals 2. You can start by isolating either x or y. I'm going to start by isolating x because that means I add y to both sides, and I get x equals y plus 2. Okay, again, I've isolated it, and I have all positives. Kind of a win-win here. So now what I do is I take what my now x value is, right? This is a solution for my x value. I now have that, and I go plug it back into the first equation, original first equation. Okay, don't plug it back into the one you just worked with. Plug it back into one you haven't touched yet for x. So now instead of saying x, I have y plus 2, so substituting y plus 2 in for x. Now I have to follow with the rest of the equation, which is plus y equals 4. I always advise to put parentheses around what you substituted in, because sometimes there might be a number outside with that coefficient that you have to distribute. Sometimes there's a negative that you want to distribute. You have to ensure that when you do substitute that in, you substitute it in as a true x value, so that any distribution, multiplication, subtraction that needs to happen will still happen to that entire term. From here, there's nothing for me to do with that this time. So I'm actually just going to go ahead and I'll bring you guys a little bit closer. It might be a little hard to see. We're just going to go ahead and combine like terms. So I have, oh, this should be a y, plus y equals 4. Okay, so y plus y is 2y, plus 2 equals 4. Okay, and again, elementary level, algebra 1 level stuff here, guys. We're just trying to solve for y. So subtracting 2 to get 2y equals 2, divide by 2 to get y equals 1. Okay, so a lot of this is really just solving two-step equations, especially when we're just dealing with linear systems of equations, mostly just two-step solutions. When you have a y value, that's awesome, but I still want to find my x. Okay, I want to find both x and y always. So what I can do now is take my current y value, plug it in for any three of these equations. This one's my easiest one because I already have x isolated. So I just have to pop y in, and then I have my x value. I could have plugged that in though to the first equation, the second, or this manipulated second. All three of them would have worked. This one is just slightly easier, and I like to go with the easier. This gives me x equals 1 plus 3. Sorry, I said the answer. 1 plus 2, or that x equals 3. So one thing I will advise you of is would like to write these in coordinate pair. A lot of times you're going to see this on like an SAT, and it's going to have like this long, like complicated explanation and directions with it that say like, solve the systems of equations using, or find a coordinate pair that solves, that is a solution to the systems of equations, and do this by using substitution or elimination, and like it just has this whole long explanation, and it simply is asking you to do this. So they want you to write it in a coordinate pair most times. My x was 3, my y was 1. What you should know is you can always check yourself. So I can go back to equation 1 and say, well, what if I don't trust myself? What if I'm not sure whether or not I got this right? You can say, well, let me plug them all back in. So my x value was 3, plus my y value is 1, equals 4. 3 plus 1 does equal 4. So yay, I got the right answer. Not only can you check yourself algebraically, you can also check yourself graphically. Okay, so I'm going to erase some of this work. If we go back to our two original equations, was x plus y equals 4, and let's see, x minus y equals 2. What I need you to do first is write these into terms of y. So I'm specifically telling you I need these all with y isolated. So in this case, we'll just subtract x to give me y equals negative x plus 4. This case, we're going to have to subtract x, but I get negative y equals negative x plus 2. So there's one additional step, and I have to multiply by negative 1. Again, I want y isolated, not negative y. So y equals positive x minus 2. So here's our two big isolated equations. Now I need you to do is go graph this in your calculator. Okay, so if you hit that y equals button, you will get brought to a page. You can always enter as many functions as you want. They'll all get graphed at the same time. What I would say is put this into your y1 and this one into your y2. If you flip-flop that, that's fine too. I'm just giving you parameters to put one of them in y1, a second one into y2. And then you can hit graph, and what you should see coming up, let's see, 1, 2, that might be a little bit too straight. This one definitely won't be accurate, but okay, so this point, ooh, definitely not accurate. Just act like that is. This point should be at 3, 1. Okay, so what's the significance of that? We said our solution was 3, 1. So what happens is when you have a solution algebraically, graphically, that solution is represented by an intersection. So at any point when these functions intersect, they have a solution at that point. If they never intersect, they never have a solution between those two different equations. If they intersect multiple times, they have multiple solutions within that system. And that is possible. So in this case, I can visually see on my graphing calculator, once I've graphed these, that, yeah, that's at 3, 1. Like, I can see that, it's fine. What if it was some decimals though, and you want to be able to still check your answer? What you would want to do is go to the second button over to trace. Okay, so second trace. Trace is along that top, those top like 5 tiny little rectangle buttons. Second over to trace. There is a button, it's about 5, not a button, an option, about 5 options down on most calculators that says intersect. You're going to scroll down to that and hit enter. On older calculators, it pops up what looks like a little spider. On my new ones, it looks more like a flower, but whatever it is, you can see it about probably right here on your graph. All you have to do is hit enter. And then this one stays, but you magically see another one pop up over here. Okay, so we have both lines having some bounds set here. What they're saying is you're focusing on this line and this line, and you want to see where those two lines are intersecting at. Your calculator is really smart and it likes to put them right next to that intersection, and it does most of the work for you here. Okay, so this one popped up, you hit enter, then this one popped up, you hit enter again. Only now you have to enter a third time. Nothing happened, nothing popped up, but you should have hit your third enter, and then in the lower corners, you'll see x equals 3, y equals 1. That's a really crappy line. X equals 3, y equals 1. To solidify that, yes, that was your intersection, so that was your solution. I won't focus as much as on this graphic part of it, but it is important to know that when they intersect, that is the solution. And you will actually see plenty of those come up on SAT. I think there was a kind of crazy question last year about that some students came and talked to me about after they were graded, of course. All right. So I have 2 more examples for you. This is your, again, elementary basic level example. Not a ton of complicated things going on within it. It is your standard, like on a normal substitution basis. You will isolate, substitute in, solve for one variable, pop that solution back in, solve for your next variable, and you're easily done. Except when it's not quite as easy, when there's not just one easy solution, there is another way you have to do some of these. I'm going to show you both of them. One is the 2 solutions case. A second one is the no solutions case. So in this 2 solutions case, we have a quadratic and a linear. So equation 1 is x squared plus 4x minus y equals 7. And 2 is 2x minus y equals -1. So as always, which one do we want to deal with first? If you have a quadratic and you have a linear, skip the quadratic, go straight to the linear. It doesn't really matter how gross the linear is. Solving and isolating this one's always going to be nicer and much more easily manageable than dealing with this quadratic. So I'm definitely going to work with equation 2. Now I have to decide which variable specifically I want to work with. I could isolate the x, but then I'm going to be dividing a whole thing by 2, so I'm going to have a fraction that's going to be even worse, and I really don't want that. So I'm going to isolate this y, meaning subtracting 2x to get -y equals -2x minus 1. We want a positive y always. So multiplying by a -1, dividing by -1, whichever makes more sense to you. Y equals positive 2x plus 1. Again, multiplying by that negative flips all those different signs around. Okay, so every negative flips to a positive. So here I have my y isolated for. Okay, now I have to deal with this portion of it and decide where to substitute that back into. This is a y value. I can't substitute back into the one I just got done with. So I have to substitute back into this quadratic for y. So writing out my new equation, I keep the x squared, keep the 4x, and keep the negative. Now open up my parentheses. Instead of y, I have 2x plus 1, close that parenthesis, and it all equals 7. Okay, so here you can see why these parentheses were really important. When I'm starting to solve this through, I have to first deal with the fact that there's a negative outside of this parenthesis. That negative distributes to everything within that parenthesis. So it's -2x, -1 equals 7. I keep solving this down, combining like terms, giving me x squared plus 2x minus 1 equals 7. And when we're dealing with a quadratic, every time you have had to deal with a quadratic in your whole life, you are never able to just solve for x how you normally would. You can't just subtract some things off and divide by some things and add, and then all of a sudden you have an isolated variable like we do here. When you have an x squared and an x, you can't solve for that x variable when you have two different kinds of degrees. Instead, what we do is we factor. Okay, so because I have an x squared and an x, I know that I can't solve for it like I normally would. So I have to factor, meaning it has to be set equal to 0. In order to do that, we're going to subtract 7 from both sides, giving me x squared plus 2x minus 8, negative 1 minus 7 is negative 8, equals 0. If you forgot how to factor, when you're factoring a trinomial like this, it pops up to 2 parentheses with x in front, and you have to decide what numbers come behind that. So those numbers are obtained by deciding what two numbers multiply to negative 8 and add to positive 2. So because I have negative multiplication, but I'm adding to a positive number, I know that one of them has to be positive and one has to be negative. So now I can start thinking about, all right, factors of 8, 1 and 8. Could I ever get down to 2 between 1 and 8? The answer is no. What about 2 and 4? Between 2 and 4, they multiply to 8. And if I have a positive 4 and a negative 2, those do add to 2. So my numbers then, positive 4, negative 2. I could flip-flop the order and say negative 2 over here, positive 4 over there, just ensuring you keep the sign the same. It doesn't matter which order they go in. Taking each of these and setting them equal to 0 now. Okay, this is where that two solutions part comes in. Because I have to take each of these parts, right? This is a solution that needs to be solved for. This is a solution that needs to be solved for. I'm going to have two x values, one being negative 4, the other being positive 2. Once I have those, now I have to say, well, now go find my y values, which will be 2 total y values. So setting this up, my first one, I'm going to use this equation down here. Again, it's just easier. I could use 1, 2, or this one. So y equals 2 times negative 4 plus 1, and y equals 2 times 2 plus 1. And I want to remind you, this is an x equals negative 4, and this is an x equals 2. It's really important that you keep the corresponding x value with its y value. You don't want to mix up those according to pairs. Solving here, y equals negative 7, here y equals 5. So my two coordinate pairs is negative 4, negative 7, and 2, 5. Okay, again, I can go check these with algebraically, just substituting these values back in. I'm going to remind you how to go do this graphically. So let's get rid of some of this. All right, what I need to do, oh shoot, I should have left this. Sorry, I'm putting back the work that I just erased. Okay, the reason I'm leaving this up here is you already did the work to isolate the y in this equation. So I'm already like, oh, that's easy. This one is y equals 2x plus 1. That was really easy. Okay, the only other one in order to put this into a calculator that you have to isolate is this one up top. So if we start thinking about what this would look like, I would have to subtract my x squared and my 4x, which would give me negative y equals negative x squared minus 4x plus 7. Oh, yeah, that's right, okay. And then multiply by negative 1 to get y equals positive x squared, positive 4x minus 7. So again, here's one, here's the other. y1, y2. Go to y equals in your calculator. I'm going to draw a really rough sketch of this. Really rough. Okay, it looks awful. I don't know exactly what you're gonna see on your calculator, but the gist of this is you should be having an intersection point over here at 2, 5. Down here, you should have one at -4, -7. If you're not positive, I want you to again go to second, trace, down to intersect. Only this time, you're gonna have to do that process twice. You look at those little spiders, flowers, whatever they are, to pop up around one intersection, and you can calculate that, hit your enter, and the third time hit enter, and pop up -4, -7. You can say, wow, I did that one right. But then you've only proven that this one point is right. You have to go through again and say, second, trace, intersect, and go calculate it for your second intersection to make sure that both of these intersections are correct. All right, last and final one, the no solution case. So if you're looking at this graph currently and you say, well, 2 solutions, 2 intersections, the last graph, 1 solution and intersection at 1 point, no solution has to mean that they don't intersect at all, which is a really easy one to prove. Graphically, algebraically, it might look a little bit different, maybe a slightly more complicated version of what you've seen. So no solution. Okay, equation 1, -x plus y equals 4, 2, x squared plus y equals 3. Okay, just like last time, dealing with these 2 equations, I'm thinking I'm going to want to go to this first equation, okay? Quadratic down here, a linear function up top. Not only that, this one just looks really easy to isolate for. But anyways, because that's quadratic, I start with number 1. Now to determine which variable. When I'm looking at this, I could so easily add over an x, and that gives me all positives. So because I love positives, and we tend to make a lot of mistakes when we deal with negatives, deal with those positives as much as possible. Now I have a y value. I'm going to take this y value, put it up in top. No, sorry, I'm so used to going all the way to the top. We just dealt with the top one. You go to the one that you haven't dealt with yet, which would be the second one in this case. So y. Giving me x squared plus x plus 4 equals 3. Always in parentheses in this case, there's nothing to distribute. So I can give myself x squared plus x plus 4 equals 3. So you might already be seeing that I put quad form on the guided notes for a reason. And you're probably like, oh my gosh, why'd you put that on there? I don't want to have to do that. Like, what do you said this was going to be not that bad. Promise you, not that bad. So as you have quad form given to you, it won't be horrible. So again, I have an x squared and an x. I'm not going to be able to solve this generally just by subtraction, division, and addition. So I have to get all my terms on one side by subtracting 3, giving me plus 1 equals 0. Okay, collect all the terms on the one side. Then I say, can I factor? Meaning, are there 2 numbers that multiply to 1 and add to 1? So your first instinct is like with 1 and 1. Okay, yeah, 1 times 1 equals 1. 1 plus 1 equals 2. And then you're going to have someone say, well, 1 times 0, like that adds to 1. Yeah, it adds to 1, but it also multiplies to 0. So it's not factorable. When something's not factorable, you have to go back to old trusty quad form. I want to remind you that it looks like ax squared plus bx plus c. So it just goes straight in order. A is coefficient to your quadratic term. Okay, so this x squared. There's technically a 1 out in front of there. So my a equals 1. B is the coefficient to your x term. That is just a 1 again, so b equals 1. And then a really weird case here, c is your constant, so here c equals 1. Not often you see all variables being the exact same value, but it does happen. So let me spin you a little bit. We want to do quad form over here. Okay. Let me get this erased. All right. So quad form is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, something you would have done plenty of times before. Geometry, algebra 1, algebra 2. You probably hated it every time you did it, but it's just a plug and chug. You have your a, b, and c, and you just have to plug them all in and just start solving. So eventually, I'm still thinking like, well, how am I going to get this to be no solution? Why is it going to be no solution? No solutions are either that you end up at the very end with a 5 equals 2, and you know those aren't equal. Or this is the other case. So I have a negative 1 for negative b plus or minus 1 squared minus 4 times 1 all over 2 times 1. We start simplifying. Negative 1 plus or minus 1 minus 4 all over 2. Giving me negative 1 plus or minus negative square root of negative 3 all over 2. When we have, and this is like the punchline, when we have a negative number and a square root, what happens? We don't like negatives and square roots. So what we have to do is we have to take that negative out and make it in the form of an I. So this would become negative 1 plus or minus I positive square root 3 over 2. Only do imaginary numbers graph on a real axis? Answer is no, they don't. Imaginary numbers are not visible on a real XY coordinate plane. So because of that, an imaginary number means it's not a real solution. So imaginary, not real, no solution. And that'd be the kind of like explanation I would ask from you. Imaginary, not real, no solution, not happening. Okay. So at that point, I don't have to go try to find a y value because I can't. I'm not going to use this horrifically disgusting imaginary number to go find my y value, especially when I'm already saying, I know because of this, there's no solution. I don't need to go find a corresponding y value. And I wouldn't ask you to, I wouldn't want to do that. So graphically, again, if you want to go through and solve this graphically, you would want to isolate, which we already did here. Our solution number 1 goes down to y equals x plus 4. And this one would simplify down to y equals negative x squared plus 3. If you graph these, again, you'll get a really rough, this is rough again, but this is about the graph you'll get. This is going to cross through at positive 4. This parabola comes up and goes about to positive 3 and then back down. And you can see there's no intersection. Okay, if you go down, that parabola keeps going down to negative infinity, and that line keeps traveling to negative infinity, but they won't cross paths because they're traveling at different rates. Over here, this is going straight up, whereas the parabola comes back down, and they don't intersect. No intersection means no solution. Graphically, no intersection. Algebraically, imaginary number. And again, if I had something like, whereas and I ended with 5 equals 4, we know that those things aren't equal, then you could also say no solution. That's another case that can happen. This quad form into an imaginary number, though, is one of the more common ones. Okay, so that is 7.1, all things substitution. Again, more common is going to be a one solution case, just solving maybe even with the quadratic, but again, going into a not with quadratic, sorry, solving with maybe more complex linear functions, but not getting into that two solution or no solution. But you do have cases where those are going to happen. So less common, but they do happen. Okay, thank you.